Hello everyone, I'm Jingfan Zhang and I'm a committer of OmmiRuntime community. The topic I'm going to share today is about OmmiRuntime. It's a common runtime framework for analytics engines. This is my agenda today. I will introduce the modern analytics ecosystem and explain why it needs a new modern OmmiRuntime solution. Then I will introduce the OmmiRuntime core technology, OmniJIT. Finally, I will describe the status and future work of OmmiRuntime. According to the European HPC research priorities, heterogeneous computing hardware becomes the mainstream, and the computing power has been deeply involved in the entire data processing process. So more and more new data processing framework use the LLVM technology to accelerate computing by the hardware, like MIT high performance optimization based on Rust and LLVM. Stanford high performance runtime is also based on LLVM. Let's see how the current analytics engine adapt to this trend. Most of engines optimize themselves. This local optimization cannot be reused by other engines. So each engine needs to be optimized independently. For example, Spark provides whole stage coding to improve the performance, but this optimization point cannot be used by Presto or other engines. We can think about this. Can we have a common framework to support different engines? Therefore, the goal of OmmiRuntime is code once and run fast everywhere. OmmiRuntime shares the optimizations across different engines and support accelerator computing by different hardware, like ARM, TPU, DPU, x86, and FPGA, and so on. Let's see the details of OmmiRuntime. The OmmiRuntime design principle are as follows. First, portable across platform to support different analytic engines. And it must be easily to integrate. Second, provide a single development framework, allowing operator developer to easily develop operators. Third, the operator can be automatic computer-aware optimization by the OmniJIT. And the OmniVector will provide a kernel memory structure of data, enable operator to process data more efficiently. Fourth, portable across hardware to support different computing hardware. Before we introduce the OmniJIT, we need to know why we need high-performance operators. Let's look at the TPCH Circle 1 statement. This statement uses 4 operators. Table scan operator load the data from the data source. Filter and projection operator do the filter and projection. Hashi aggregation operator group and sum the data. Order by operator order data. The last 3 operators are about computing that account for about 60% of query time. Just think about this. If we have high performance operators to reduce 6% to 10%, the performance of this query statement can be improved by twice. That's why we need high-performance operators. So, how do we implement the high-performance operators? Let's look at the operator optimization in current engines. The operator performance conflicts with the development. There is no way to achieve high performance and easy development at the same time. Let's talk about this. Many analytic engines have used operator optimization, such as Impala Circle Engine for Hadoop, to improve their performance. Impala's approach reduced the instruction count by 4 times and the branch by 3 times. Impala dynamical generator expression iterator by LLVM build API. Impala also provide pre-built functions to simplify the operator optimization. And the LLVM build API groups this pre-built function into more complex operators. This approach provides good performance, but is not so friendly to operator developers. WildAI is another attempt to simplify operator optimization. The analytic engine will generate WildAI, which is then compiled to the final bytecode using LLVM. The syntax of WildAI is very similar to a cursor in Rust program language. However, there is no debugger for the WildAI. Another technique is used by Spark and Presto. Spark uses Genino to generate Java source in memory and compile them into bytecode classes that can be executed in JVM. The code generation process combining operator logic into a big loop that reduces function evocation overhead and memory copying in intermediate result. Presto is similar. Query generator class converted into high-level errors and use JavaScript to optimize them. This approach does not bring the best performance and is not good for development and debugging. OmniJIT is used to create operators using high-level languages and specialized runtime, achieving similar or better performance compared to traditional JIT approaches. Bridging high performance with ease of development, OmniJIT provides a just-in-time tool to engine development. OmniJIT enables developers to use high-level language to implement the operators. The developers focus on operator logic instead of optimizing the operators. They use C or C++ to implement operators. The development cycle is fast and easy to debug. Then, the operator is integrated into a target system. And the OmniJIT API is invoked to provide context information during runtime. The operator is automatically optimized by OmniJIT and has high performance. Totally, the only thing you need to do is use C or C++ to write operator. Do not care how to optimize the operator. It's so easy to development. And then you can get a high performance operator. The life cycle of an operator is split into two stages. A pre-processing stage that generates operator IRs, and a running stage that optimizes len. In the pre-processing stage, no runtime or hardware-specific optimizations are used. Once the operators have been coded, the source is then passed into preprocessor. The preprocessor performs high-level syntax validation and operator conformance check. The generated operator IR is a representation of a generic operator code at runtime that is as low level as possible, but at the same time high level enough for future optimization. In the current implementation, the preprocessor backend uses LLVM to generate the AR. However, we have designed a framework that is not depend on single compiler backend. We plan to add additional backend to support shield values needs that LLVM cannot fulfill. In the second runtime stage, analytic engine want to evoke the operator to process the data. It provides the runtime information to OmniJIT, such as parameters, statistics, data layout, and hardware information. Then the OmniJIT specializes the AR and generate high-performance bytecode that can be directly invoked by the engine. The bytecode will be cached for use the stem operator. Here is an example of how OmniJIT specializes operator. The blue block is a piece of code to process data based on the type. The preprocessor generator AR, and in this AR, we can see that there is a judgment branch here. This judgment is required for processing each load of data. So there is a performance overhead. If the data type is provided to the OmniJIT at runtime, the OmniJIT will help you to remove the judgment branch from the AR to form the following optimized operator. This is a simple example of parameters specialization. Parameters specialization also support instruction combination and code inlining. In addition, OmniJIT support optimization based on data layout. Modern CPU, GPU, and FPGA can take advantage of vector operations, where the same operation is executed on large amounts of data. But performance may deteriorate if long types of operations are used. In order to avoid this, the layout optimization stage utilizes the data layout information and pick the best specialization optimization for the data processing. Another point is statistical information, such as data cardinality, can be used to select a specific Hasse algorithm. And it's also possible to create more hardware-specific version from the LLVM IR that make the compiler can apply more optimizations to a program once it knows the hardware details of runtime machine. This information is captured at runtime and allow OmniJIT to tailor specialized versions that are optimized based on the hardware specification of each node running on a cast. We use C++ to implement the OpenOken operators and optimize this operator across the OmniJIT. All operators are executed 1,000 times over 100 GB of data for each thread allocated. We first run the C++ native operator over the data. Then we executed the same operator within OpenOken using the Java operator. We can see later optimized operator is several times better than the OpenOken operator. And we have integrated operators into OpenOken. And they improve the performance by 30 to 40%. Currently, OmmiRuntime supports Java, Scala, C, and C++ binding, and support more than 10 operators of Circle Engine, and support basic types such as boring int, long, double, and retry. And OmniJIT supports parameters specialization. In the next step, we will support Python and Go. In addition, we will try to simplify operator development. We also want to implement HPC and machine learning operators. For the OmniVector, we'll support complex types and themed optimizations. And OmniJIT will support operator fusion, statistical specialization, hardware specialization. Totally, OmmiRuntime is a framework for data-driven specialization, which can be used in development in the next generation big data processing. Our goal is to build an OmniReport that contains operators in different scenarios and support different engines. So it's a lot of work need to do. So welcome to help us implement more operators and enrich the OmmiRuntime ecosystem. Finally, you can learn more about the work on the progress of OmmiRuntime from the OpenOken community. So let's talk about my topic. Thank you.